Have you ever found yourself needing to um, quickly get up to speed on some really complex topic? Maybe for work, maybe just because you're curious, you hit search, right? And bam, thousands of results. But, well, sometimes those traditional methods, they just fall short. They don't quite give you the accurate, nuanced answers you actually need. So today, we're doing a deep dive into the evolving world of retrieval augmented generation, or RAG systems, and specifically why sometimes that simple vector search approach, it just isn't enough, especially when you're dealing with really dense, complicated enterprise knowledge.
That's exactly right. Our focus today is on the journey of a company called Ryder. They've really been pushing the boundaries on building highly accurate OR-reach systems. We're pulling insights from a talk by Sam Julian. He's their Director of Developer Relations. The talk was called When Vectors Break Down, Graph-Based RAG for Dense Enterprise Knowledge. So, our mission here is to unpack why traditional vector search hits limits, explore the promise, and importantly, the challenges of graph-based ARG. And we'll see how Ryder basically innovated their way to AI applications that are highly accurate and, crucially, have very low hallucination rates.
Right. So let's set the scene a bit. After ChatGPT kind of exploded, there was this huge gold rush, wasn't there, around vector databases. Everyone was just incredibly excited about vector search for R. It felt like the solution.
Absolutely. It was everywhere.
But pretty quickly, the industry started to realize that maybe vector search alone isn't quite, well, insufficient for sophisticated retrieval, as the thinking goes now,
Yeah.
and that we're probably going to need, multiple strategies beyond simple vector similarity.
Yeah, the initial hype cycle cooled down a bit when people hit real-world problems.
Exactly. It was like a sprint,
Yeah.
but now we see it's more of a marathon, needing a bigger toolkit.
That's a great way to put it. And Ryder, they definitely encountered this. They ran into two core problems pretty early on that showed vector retrieval wasn't going to be enough, especially for their clients with these massive, dense knowledge bases.
Okay, where were those?
So the first one was getting inaccurate answers from naive chunking and nearest neighbors.
Naive chunking. Do you mean just chopping up the text?
Pretty much. You break the text into smaller pieces for the vector search, right? But doing that, well, it can easily strip out critical context. Sam Julian used a great example. The Apple founding timeline. Imagine a document talking about Apple's history. A RORGA system using simple chunking might mistakenly say the Macintosh was created in 1983.
But it was 84, right?
Exactly, it was 1984. But why the error? Because the text chunk that mentions the Macintosh might also mention the Lisa computer being introduced in 1983. The vector search just sees the terms close together in the chunk. A human reads it and understands the distinction instantly, but the RG system gets confused.
Ah, okay. So proximity isn't always meaning. It loses the relationship between the dates and the products.
Yeah.
That's a subtle but really critical failure.
It really is, especially when accuracy is paramount.
What was the second major issue they hit?
The second one was what they called failure with concentrated data.
Hmm.
Think about, say, a mobile phone company. They've got maybe thousands of internal documents, spec sheets, marketing docs, support articles, and they all use very similar language, right? Terms like megapixels, cameras, battery life are everywhere.
Yeah, I can picture that. Very dense, very repetitive terminology.
Exactly. So now, if you ask the RAG system to compare two specific phone models, maybe Model X versus Model Y, vector search really struggles. All the documents, their vector embeddings, they look incredibly similar because the terms are so similar. It can't easily pick out the distinct features or comparisons for just Model X versus just Model Y.
It's like everything gets blurred together.
Precisely. It leads to confusion for the RAG system. It can't differentiate effectively, so you get muddy or inaccurate answers, like trying to find a specific grain of sand, as Sam put it.
That makes total sense. If the embeddings are too similar, how do you find those crucial differences? Okay, so given these vector search limitations, where did Ryder look next? What was their hypothesis?
Well, the team pivoted. They started thinking about querying a graph database instead. The idea was to use keys from the graph to pull back relevant documents.
A graph database.
Okay.
So focusing more on the connections.
Exactly. The core idea is that graphs excel at preserving relationships within the text. How entities, concepts, dates, products, whatever, how they actually connect to each other. And preserving those relationships, that provides more context to the model, which in turn directly helps improve the accuracy. The model understands how things relate, not just that they appeared nearby.
That feels intuitively right. Context through connections.
And what's really interesting, Sam mentioned that when Ryder started exploring this path, maybe a couple of years ago, there actually weren't that many people doing graph-based R.
Really? So they were pretty early adopters on this.
Seems like it. Which really underscores their approach. They weren't just chasing the latest tech trend. They hit a problem with vector search for their specific needs. And they looked for a solution focused on that problem, which led them to graphs.
That's a really important point, isn't it? That problem-first mindset versus just, jumping on the latest bandwagon. For listeners facing complex tech choices, what's the real difference there?
It fundamentally changes how you approach things. Instead of starting with, oh, cool, let's use technology X, you start with, what exactly is the customer struggling with? What outcome do they need?
Hmm.
For Ryder, it meant they weren't afraid to say, okay, pure vector search isn't working for this dense data, even when it was hyped. And crucially, it meant when they did try graphs and hit new problems, which we'll get to, they didn't just abandon ship, they kept focusing on the user outcome and adapted again. It's about being flexible and outcome-driven.
Okay, so graphs look promising, but you mentioned they hit new problems. It wasn't an instant fix then. What kind of hurdles did they face when they first started implementing graph-based drag?
No, definitely not a silver bullet right away. Remember, this was a couple of years back, and the tooling and best practices were still evolving. Ryder ran into 4 specific, significant challenges.
Okay, let's hear them.
First, just the process of converting raw data into a structured graph at scale proved difficult and expensive. Taking all that unstructured text and forcing it into a strict node-and-edge graph structure. That's non-trivial, especially with huge volumes of data.
I can imagine it's a big data transformation task.
Second, as their graph database started to scale up, the team hit limits of their expertise and encountered cost issues. Graph databases can be powerful, but they also require specialized knowledge to manage effectively, and they can be resource-intensive, which means costly.
Okay, so scaling brought expertise and cost headaches. What else?
Third, the query language they were using, Cypher, which is common for graph databases, it actually struggled with the advanced similarity matching needed for their use cases. They needed sophisticated semantic search capabilities, and Cypher wasn't quite flexible enough for what they were trying to achieve at the time.
Interesting. So the query language itself became a bottleneck.
Yeah. And finally, the fourth challenge was a bit counterintuitive. They noticed that the large language models, the LLMs themselves, were often performing better with text-based queries rather than complex graph structures fed directly to them. The LLMs seemed more comfortable, if you will, processing straightforward text.
Wow, okay. So they pivoted to graphs to solve the vector search problems, only to run into a whole new set of challenges with data conversion, scaling, cost, query limitations, and even LLM preference.
Exactly.
That must have been a frustrating point. But you mentioned their first principles thinking. This sounds like where that really came into play, right? They didn't just double down on the struggling tech stack.
Precisely. Instead of trying to force a square peg into a round hole, they stepped back. They asked, okay, what problem are we fundamentally trying to solve here? And what tools and skills do we already have that we can leverage? They were willing to challenge their own path forward.
So let's dig into that adaptation. How did Ryder tackle these specific graph challenges? How did they use their internal skills and that customer focus?
They came up with some really clever, inventive solutions addressing each challenge. For that first hurdle, the challenging and costly data conversion, they didn't just grab an off-the-shelf tool. Instead, Ryder actually built their own specialized model.
Ah, an in-house solution.
Yes, and one designed to be efficient, capable of running on CPUs or smaller GPUs, which is important for cost and scalability. This custom model was specifically trained to map this data into graph structures of nodes and edges. And crucially, they combined this with better context-aware splitting and chunking. So they didn't just map the data, they did it in a way that preserved the vital context and semantic relationships better than standard methods. It gave them much finer control.
That's really smart, building the exact tool they needed instead of compromising. That speaks volumes about their commitment. Was that a big decision resource-wise?
I imagine it was a significant investment, yes. But again, that problem-first mindset drove it. They saw a gap for their specific kind of dense data that existing tools just weren't filling adequately. The investment gave them a unique capability.
Okay, so that addressed the data conversion. What about the scaling, cost, and expertise issues with the graph database itself?
Right. For those, they adopted a really neat hybrid approach. Instead of putting everything directly into a native graph database, which was causing the scaling and expertise issues, they decided to store the data points as JSON in a Lucene-based search engine.
Okay, wait. So they took the graph structure and stored it as JSON in a search engine like Elasticsearch or Solr.
Essentially, yes. They converted the graph structure, the nodes, the edges, the relationships, into a JSON format. And then they indexed that JSON within a familiar, scalable search engine technology. This was brilliant because their team likely already had expertise in managing Lucene-based systems. It allowed them to easily handle large amounts of data without any performance or speed degradation using tech they were already proficient with. They sidestepped the need to become deep graph database experts overnight and leveraged their existing strengths.
That is clever. Using the structure of a graph, but the scalability and familiarity of a search engine. Okay, so they've tackled data conversion, scaling, cost. But what about the query limitations and the fact LLMs seem to prefer text? This feels like where the really big breakthrough needed to happen.
It absolutely was. This is where things get, as you said, really interesting. The team didn't just look at recent RAG variations, they went back to the original RAG paper itself. Deep dive into the fundamentals.
Okay, what did they find there?
They noticed something crucial. The original paper didn't actually frame a RAG purely in terms of, stuffing context into a prompt, which is how many people implement it now. Instead, the original research proposed a two-component architecture with a retriever and a generator. And digging into related research around efficient transformers led them to a technique called fusion and decoder.
Fusion and decoder. Okay, unpack that for us. That sounds technical, but important.
It is. Think of it like this. When you have lots of retrieved passages, checking how every piece relates to every other piece gets computationally very expensive, very fast. It scales quadratically, meaning the workload explodes as you add more data. Fusion and decoder offers a smarter way. It processes the passages independently in the encoder first. This breaks down the complexity, making it scale linearly much, much more efficiently, like handling tasks one by one instead of all at once in a tangled mess.
Okay, so it processes things more efficiently up front.
Right. And then, in the decoder stage, it intelligently brings all that processed information together for better evidence aggregation. It figures out how the pieces fit together to support an answer. Sam Julian described this as a big efficiency breakthrough that led to lots of state-of-the-art performance in research benchmarks.
Wow, okay. Efficiency and performance. But how did the knowledge graph part fit back in? They stored the graph data in the search engine.
This is the key insight Writer had. They realized they could integrate knowledge graphs with Fusion and Decoder. The knowledge graph, even stored as JSON in the search engine, provided the crucial understanding of relationships between the retrieved passages. Fusion and Decoder handled the efficient processing, and the knowledge graph provided the semantic context to make sense of it all. It helped the decoder aggregate evidence more effectively, understand the nuances, and synthesize better answers. It wasn't just faster, the graph structure helped it be smarter.
So the graph data acts like a map for the fusion and decoder process to navigate the relationships between the retrieved text.
That's a great analogy. It guides the aggregation process. Writer built their own implementation of this combined approach, and Sam said this became the final piece of the puzzle. It really helped our hallucination rate, really drove it down.
Incredible. So combining the graph structure, stored efficiently, with an advanced processing technique inspired by fundamental research. That was the secret sauce.
It seems that way, a combination of clever engineering and deep research insights.
So the big question then, does this complex, multifaceted system actually deliver in the real world? What about performance? Did they benchmark this?
They did. They conducted benchmarking, I believe it was last year, using a standard data set, Amazon's robust QA data set. They tested Writer's system, the one with the knowledge graph integration and fusion and decoder, against 7 different vector search systems.
Okay.
So a head-to-head comparison.
The results.
The results were impressive. Writer's system achieved the best accuracy and the fastest response time among the systems tested.
Best accuracy and fastest. That's pretty compelling evidence.
It really is. And beyond benchmarks, this advanced R unlocks very practical, customer-facing features that simpler systems struggle with.
Like what? What can users actually do with this?
Well, for one, because the system inherently understands and preserves relationships and context, it can actually expose the thought process. It can show users the snippets and the subqueries and the sources for how the RAG system is actually getting the answers. This isn't just a black box. They can offer transparency either via an API or directly in their product.
Oh, wow, that's huge. So you don't just get the answer, you get the show your work part. That builds a lot of trust, especially for complex enterprise use cases.
Exactly. Trust and transparency. Second, The system excels at multi-hop questions.
Multi-hop, meaning questions that require connecting information from different places.
Precisely. It can reason across multiple documents and multiple topics without getting lost. It can answer those really complex questions that require synthesizing information from various sources, something basic retrieval often fails at.
Okay, that's a big step up in reasoning ability. Anything else?
Yes. Thirdly, it handles complex data formats much more effectively. Situations where perhaps the answer to a question is split into multiple pages of a document, or where the user's query uses slightly different terminology than the source documents. Because of that underlying graph structure providing context and the sophisticated aggregation from Fusion and Decoder, it can piece together the correct answer even in those ambiguous, tricky scenarios where vector search might just return irrelevant chunks.
Accuracy, speed, transparency, complex reasoning, handling messy data. That really covers a lot of the pain points we started with.
It really does seem to address those core limitations head on.
So bringing this all together then,
Right.
what would you say is Writer's main takeaway from this whole journey into graph-based RAG?
I think Sam Julian summed it up well. The main point is that there are many ways that you can get the benefits of knowledge graphs in RAG. It doesn't have to mean using a specific graph database technology, especially if that comes with challenges. It could be, as they showed, through a search engine or potentially other creative approaches. The core principle is leveraging the power of relationships that knowledge graphs represent, however you choose to implement and store that structure within your RAG system.
So focus on the principle capturing relationships, not necessarily one specific tool.
Exactly. And related to that, the principles that really drove writer success here seem widely applicable.
What were those again?
Sam highlighted three. First, relentlessly focusing on the customer needs instead of chasing hype. What problem are we really solving? Second, staying flexible based on the team's existing expertise. Leverage what you're already good at. Don't force a technology that doesn't fit your team's skills or budget if there's another way. And third, critically, allowing research to challenge initial assumptions. Be willing to go back to basics, question the standard approach, and adapt based on what the evidence and fundamental principles suggest.
Problem first, flexible, and research-driven. That feels like a powerful recipe for tackling complex challenges in almost any field.
I agree. It's about being adaptive and grounded.
It really makes you think. As you, our listener, consider the problems you're tackling in your own work. What assumptions are you holding on to? Could any of them be challenged by digging a bit deeper, maybe going back to some fundamental research or first principles? It's worth considering how that kind of problem-first, adaptive thinking might unlock some unexpected, maybe even breakthrough solutions for you too.